On November 7, 1940, just 4 months after it opened, the Tacoma Narrows Bridge in Washington state began to shake. No earthquake, no explosion, no overload, just wind, 64 kilometers per hour of it. Within hours, the entire bridge collapsed into the water below. And the physics behind that disaster? It's hiding in every bridge, every building, every structure ever built, including the ones in your city right now.
Every physical object has what engineers call a natural frequency. It's the rate at which something naturally wants to vibrate when disturbed. Think of a swing. If you push it at the right moment, every time it comes back to you, it goes higher and higher with almost no effort. You're matching its natural frequency. Now imagine the wind doing that to a bridge, a natural frequency of about 0.2 Hz, meaning it wanted to vibrate roughly once every 5 seconds. The wind that day created vortices, spinning pockets of air that peeled off the bridge at almost exactly that same frequency. Each gust added energy to the vibration instead of damping it. This is called resonance, and it is, quite literally, a structure shaking itself apart. The phenomenon is called vortex-induced vibration. When wind flows past a blunt object, like a bridge deck, it creates alternating vortices on either side. This creates an alternating lift force. Up, down, up, down. If that alternating force matches the bridge's natural frequency, you get resonance. The amplitude grows, and the structure fails. The natural frequency of a structure depends on two things: its stiffness, how much it resists deformation, and its mass. Increase stiffness, increase frequency. Increase mass, decrease it. After the Tacoma collapse, engineers redesigned bridges with aerodynamic decks, shaped more like an airplane wing to disrupt vortex formation. They also added dampers, devices that absorb vibrational energy like shock absorbers in your car. One of the most dramatic examples is Taipei 101 in Taiwan, once the world's tallest building. It has a 660-ton steel ball suspended near the top. When the building sways in a typhoon or earthquake, that ball swings in the opposite direction, canceling the vibration. It's called a tuned mass damper. Today, AI-powered tools can simulate exactly this before a single beam is ever made. Engineers input the geometry, material properties, and wind loads, and the AI runs thousands of simulations to find dangerous resonance conditions and optimize the design. Has this happened again since 1940? More than you'd think. In 2020, the human Pearl River Bridge in China began dramatically oscillating, caught on video by drivers on it. The bridge was closed for inspection. The cause? Maintenance barriers installed on the side altered the aerodynamic profile and introduced the exact conditions for vortex-induced vibration. The fix? Remove the barriers. The resonance stopped immediately. In Nepal and across South Asia, many suspension footbridges cross mountain gorges, often in areas with strong, channeled winds. Most of these were not designed with computational wind analysis. The Tacoma failure is not ancient history for infrastructure like this. What used to take weeks of hand calculations now takes minutes. The lesson engineers took from Tacoma was not just build stiffer bridges. It was understand the aerodynamics, model the interaction between wind and structure, and never assume that because something stands still in calm conditions, it will be safe in all conditions. Every structure you will ever design has a natural frequency. Your job as an engineer isn't just to make it strong enough, it's to make sure nothing in its environment can excite it into resonance. AI tools are now making that analysis faster and more accessible than ever. And in the next video, I'm going to show you what happens when the ground itself starts to vibrate, and how AI is being used to design earthquake-resistant structures for cities like Kathmandu. If you're studying civil engineering, or you're just someone who crosses a bridge every day, subscribe, because the physics holding the world up is stranger and more fascinating than most people ever realize. Drop the name of a bridge near you in the comments. I'll tell you what its natural frequency approximately is.